In experiment 10, we're going to be looking at Newton's second law of motion, which is force is equal to mass times acceleration. Here's a diagram of the apparatus that is used in this experiment to collect the data. So consider a cart on a low friction track. So here's the cart with a metal flag attached to it. The cart has a string attached to it, which it goes over a pulley. At the end of the string is attached a hanging mass. So this hanging mass is going to be the force that is adding tension to that string and causing the cart to move along the horizontal with a specific acceleration. When we let go of the cart, what's going to happen is it's first going to go through this first photo gate, starting the timer, and then it'll go through a second photo gate, which will stop the timer. So we'll be able to see how long it takes the cart to go a specific distance between the two photo gates. We can use the distance to calculate the acceleration, which we'll see on the next slide.
All right, so we're doing lab 10 today, and that is Newton's second law of motion, where force is equal to mass times acceleration. So in this experiment, we're going to be using an air track. That's what this thing is here. So what an air track is, it has tiny holes along it, and we're going to turn on this pump. Hear it real quick. And that pump is causing the air to come through the holes. So what this is going to do is it's going to allow for less friction so that when this glider is on the track, it can move with ease. Okay? So we have the air track. We also have two timers set up, two sensors that are going to time the travel of the glider. Okay? So the two timers are set up 50 centimeters apart. So the distance on your data table will remain at 50 for every trial. Okay? So the glider then is going to be placed on the air track, and notice this glider has a rope attached to it, a little string here. At the end of the string, we're going to be attaching a little hanger. So this is where we're going to be applying that hanging mass. This hanging mass is going to change throughout the experiment. So you'll see on the data table that for each trial, the hanging mass will be increasing, because what we're going to do is we're going to be taking these little hanging masses, so here's the masses, we're going to be taking them from these spots on the glider and adding them to the hanger. Okay? Now this hanger is going to be hanging over the edge here. So what this hanging mass is it's going to be the force that is going to pull this glider. Okay, so we're going to use the hanging mass to calculate the force. All right, so when I start this experiment, what I want is for this glider to be as close to my first gate as possible. Okay, that's just going to allow for less error. Once I turn the air on, the hanging mass is going to apply force. It's going to pull this glider so that it moves through both gates. When the glider moves through this first gate, it is going to start the timer. As it continues its journey and goes through the second gate, the timer will stop when it goes through the second. So that's going to be my T1 for my first trial. I am going to do that same trial with the same hanging mass 3 times so that I can get an average. Then, for my next trials, this falls off quite often, what we're going to do is we're going to take another mass from the cart and put it on the hanger. So the reason for this, the reason we are taking masses from the cart and putting them on the hanger is we want the mass of the system to stay the same the entire time. So we have given you, in your data tables, the mass of the system. And that is the cart, the hanger, and all the weights that we are using. So this mass is staying constant because we are simply taking masses from one part of the system and putting the masses on a separate part of the system. Okay, so that's how we're keeping the mass constant. We are then going to use this data to do some calculations to figure out our calculated mass, our experimental mass, and apply that to the actual mass given to you. So let's do a trial and see how this works. So let me get my hanger. It kind of fell off on the floor here. So this would be the first trial. My two gates are 50 centimeters apart, or 0.5 meters. Okay, I have 7 grams on the hanging mass, 0.007. That's including the mass of the hanger itself. Okay, so I'm going to go ahead and turn on the air. Hopefully it doesn't glide away on me. And so I want the glider as close to the first gate as possible before I let it go. When I let it go, since there's no friction anymore, that force on that hanging mass is going to pull the glider through both gates. So the timer starts when it goes through the first gate, and it stops when it goes through the second gate. So that is how I'm getting the time on my data table. I'll do that 2 more times, and then transfer mass.
So here's the data that was collected with the experiment. You saw on the previous slide the air track itself and how the apparatus was set up to collect this data. So you can see you have 2 data tables in your lab manual. Data table 1 is the top table shown here, where we have the mass of the cart, the mass of the hanger and the slotted masses, and then the total mass of the system. Now I want you to go ahead and cross out the mass of the cart, both the gram and kilogram amounts, because we're just going to look at the total masses. So you don't need to fill in mass of cart or mass of the hanger and the slotted masses. So what I want you to do is fill in the total mass of the system at 216.2 grams. Now I also want you to fill in the kilogram amount right here, but you need to calculate that. So remember, this is a metric to metric conversion, and when we're doing metric to metric conversions, all you have to do is move the decimal point. So you can use the chart where you have KHD, DCM, in this case we're talking about a mass, so grams will go in that center spot, and you want to make sure to go ahead and move the decimal point the appropriate amount of times to convert from grams to kilograms. Now for data table 2, you'll notice we have 5 different trials. Each different trial, the hanging mass is changed. So in the first trial, the total hanging mass is 0.007 grams. And then in the second trial, the hanging mass is 0.012 grams, so on and so forth. So how we get this hanging mass is we're taking masses from the cart and putting them on the hanger. Okay? This is how we keep the total mass of the system the same throughout, is because we're not taking any masses away or adding any masses from somewhere outside of the system. We're taking them from the cart and putting them on the hanger, and both the cart and hanger are part of the system as a whole. For each trial, we recorded 3 different times. So what you need to do for this t-average column is add those 3 times together. So T1 plus T2 plus T3, and divide that by 3. So that's how you're going to get your average. You're going to add these 3 together and divide by 3. And you're going to do that for every trial. When you do that, make sure that you try to stay with sig figs. So what I mean by that is, since I went out 4 decimal places in all of these times, you should go out 4 decimal places as well in your average time. All right, now there's 2 other calculation columns. We have the accelerating force column and the acceleration column. So how do you calculate the accelerating force column? Well, for this one, the accelerating force, it's the hanger and the mass. Okay, so the force that's being applied is being applied from that hanging mass. So we're going to calculate that force. We're going to take the hanging mass in this column here for each trial. So these are the masses that we're going to be plugging into the force equation. And we're going to multiply that by g, gravity. Because since the mass is hanging, the acceleration, the rate that is affecting that hanging mass is gravity. It's like a free fall. Okay? So you want to take these masses in the hanging mass column and multiply them by gravity. And remember, the value that we use for gravity is 9.8 meters per second squared. So do that for all of those trials. Now for the acceleration column. So for this column, we're actually rearranging one of our zero initial velocity equations. So we're going to get acceleration is equal to 2d over t squared. And you can see me work through some of these calculations in the video on the next slide, but I just want to give you the equations here. So 2d, so this d is the distance, and notice we have a distance column here. So these are the distances that you're going to be plugging in, your d values in that equation. So notice the distance stayed the same for every trial. So you're going to take 2 times 0.5 for the numerator. For the denominator, this t squared, make sure you're using your average time column. So that average time column that you calculated. So you're going to take the average time that you calculated and square it for the denominator. Then you will divide those two to get the acceleration in meters per second squared. So that's how you fill in the calculation columns of the data table.
So we're going to look at Lab 10. So there's a video on Lab 10 explaining how the data was collected, and then you also have a copy of the lab with the part of the data table filled in. So what I wanted to do was supplement that and kind of go through exactly what you need to be completing on the lab and how to do so to try to kind of answer any questions preemptively. So what I have here is data table 2. And notice I don't have all the columns, I just have 3 of the columns present. The first one being accelerating force measured in newtons, and you'll notice that column is blank on your lab. So that column you need to calculate. All right, so to calculate the accelerating force, you're going to be using the gravitational force equation. So this is essentially F of W, the weight force. So to calculate the weight force, you're going to take the mass times gravity. So in the data collection video, you'll notice there was a hanging mass that was hanging over the side of the air track. And what was affecting that mass was gravity. So by multiplying those two, you're going to be calculating the force that was being used to make that glider move across the air track. So you're going to use this equation for each of the 5 trials and fill in. So since every trial had a different mass, every accelerating force should have a different answer as well, a different value. For the average time column, so that's the other column that's blank, to calculate the average time, you need to take the 3 trials of time, T1, T2, and T3, and divide that by 3 to get the average. Make sure if you are putting this entire thing in your calculator that you do parentheses around that addition on in the numerator. So you will fill that in for all of the 5 trials as well. The last column on the data table that you need to fill in is the acceleration column. This is the x-axis on the graph provided. So what I did was I took an equation from chapter 4, the distance is equal to 1/2 at squared, and I rearranged it to solve for a. So to solve for a, we're going to do 2 times the distance, and the distance is 0.5 meters for every trial, so the distance is the same in every trial, but the t average is going to be different. So I want you to take that t average that you calculated in this column over here and square it in the denominator. So for each of the acceleration calculations for all 5 trials, you'll take 2 times the distance divided by your average time squared. Don't forget the squared portion. So what I did with the graph, so the graph has been provided, you don't have to graph it, but I took these accelerating force values, and those were my y-axis values, and then I took the accelerating force values, and these were my x-axis values. So I have a similar diagram to what you will see on the provided graph, having the force on the y-axis and the acceleration along the x. And from this, what you need to do from the graph is calculate the slope. So a little reminder on how to do that, because I noticed there were some troubles in the lab 7 with calculating slope. So I just wanted to do a little refresher here as well. So you need to pick, the important part is you need to pick 2 points on this line, okay? And in the graph I provided, I only went through maybe 1 data point. Okay, so you cannot use the data points to calculate the slope. You need to pick points that are present on the line. So pick points that are easy to read. So I'm going to pick, say I pick this point here. So this will be my first point. So my x1, my y1. So this first point, to figure out what x1 and y1 are going to be, I'm going to follow this point all the way down until I hit the x-axis. Whatever value that is reading on that point on the x-axis, that is my x1 that I am going to plug into this equation right here. I'm going to look at that same point, and I'm going to follow it over till I hit the y-axis. Whatever value it hits along the y-axis, that is my y1. So x1, y1, these are going to be the 2 values that I plug in here, because this is my x value for data point 1, my y value where it hit on the y-axis for data point 1. I then need another point. My second point will provide x2 and y2. So pick a point that's on the line, follow it down and across. So following it down until I hit the x-axis, whatever value it hits upon is going to be my x2. And I'm going to follow it across that same point until it hits the y-axis, and that is going to be my y2. So this will be x2 and y2, which we'll plug in for the other 2 points in that equation. So calculate and solve. Make sure you have parentheses around both the top and bottom portion. So why are we calculating slope in this experiment? We're calculating slope. Let's look at the units of the slope. So that's going to help us understand the why. What does the slope mean? Okay, so slope is change in y over change in x. So we have y values on top and x values on bottom. But what is y? Well, to figure that out, you look at what did you plot on the y-axis. Okay, the y-axis was the accelerating force. So it was the force. What are our x values? Those are all representing acceleration. All right, so force is measured in what? So we're looking at, remember, units. It's measured in newtons. Our acceleration is meters per second squared. Okay, so let's take this a step further. What are newtons? Okay, so to figure that out, I'm going to go back up here and I'm going to look at force. So force, we said, is measured in newtons, right? Force, newtons. But how do we calculate force? We take mass, in this case, and we're multiplying it by gravity. So what is mass measured in? Mass is measured in kilograms, because every time we use mass in any of these physics equations, we've been converting it to kilograms first. Gravity then has the same units as acceleration, and it is measured in meters per second squared. So newtons is really the same as saying kilograms times meters per second squared. So I'm going to substitute this n that's in the numerator on top for kilograms times meters per second squared. And then on the bottom is acceleration, and the units on that, remember, were meters per second squared. So looking at this equation, can we cancel anything out? What it has in common is I have a meters per second squared in the numerator on top, and I have a meters per second squared in the denominator on bottom. So if they're on opposite sides of this horizontal line, they cancel. So when I'm calculating slope, what I'm really calculating is just the kilograms. And what is kilograms? Kilograms, we just said, is a mass. So I'm calculating the mass of the system by calculating the slope. So we're going to be using this to do a percent error calculation. And what we're doing the percent error of is we're going to compare the total mass of the system, which is given to you in data table 1, to the mass we calculated in the slope. So to do that, we're using our percent error calculation, where we take measured minus true. These are absolute value signs, so it's going to be a positive number no matter what. If you get negative, just change it to a positive. And then we divide that by the true value and multiply by 100 to get it into percent value. So what is our measured and what is our true? Our measured is the slope that we calculated down here. Picking 2 points on the line, getting our x1 or y1, our x2 and our y2, and plugging that in. Okay, so the slope we got is the measured mass of the system. The true value of the system is the actual mass given in data table 1. I do want to point out that notice in data table 1, you are given the mass of the system, the true mass, in grams and kilograms. So make sure that you choose the correct units when you plug it in, because you are comparing these two, so they need to be in the same units. Okay? So you're going to calculate how far off we were with our slope calculation compared to the actual slope, the actual mass given to you in data table 1. Now everyone should be getting similar slopes and similar percent errors because we're all using the same graph and the same data.
So as you saw from the previous slide with the video on it, I showed you how to calculate those columns in data table 2, and then also how to calculate the slope. So for this lab, you don't have to make the graph is provided for you, but what I want you to do is I want you to take that graph and calculate the slope by picking 2 points on the line. Okay, so make sure the 2 points that you choose are on the line. Once you choose those 2 points, as you saw in the video, you follow those points down to the x, and then that point over to the y to get your x1 and y1 values. Okay, your second point will give you your x2 and y2 values. Then you can plug those in to the slope equation, which I have rewritten again here. Making sure to put the y values on the top and the x values on the bottom. Make sure that you calculate it all the way out. Do not leave it in a fraction form. Because the slope that we're actually calculating the mass. And we're going to take that slope in kilograms and we're going to compare it to the total mass of the system that we were given in data table 1. So as a reminder from the video, the units on the slope Remember, units for the y-axis, since the y-axis is force, is going to be newtons. Newtons are kilograms times meters per second squared. Units for the x-axis, since it's acceleration, are meters per second squared. So you can see, since you have meters per second squared both in the numerator and in the denominator, that they cancel out, leaving you with just kilograms. So the slope that we calculate, the units will be kilograms, and we can compare that kilogram slope to the total mass of the system, also in kilograms. They should be close to one another, but they won't be exact because there is a little bit of friction, there is human error, so there are many possible errors in this lab. The percent error calculation, I have the equation shown here again. So the measured value, this is your slope calculated from the graph, picking 2 points on the line. The true value then is going to be the total mass of the system. Make sure you're using the kilogram and not the gram amount from data table 1. And the true also goes in the denominator. Remember, with percent error, we have absolute value signs, which means it is going to be a positive. You'll never get a negative value. If you do, simply change it to a positive. Don't forget to multiply it by 100 to get it in a percent. Whenever we calculate percent error, the units themselves actually cancel, so we only need to put a percent sign on our answer. When you turn in this lab, make sure that you are turning in both data tables, since you have calculated columns in both data tables, as well as the questions that come after the data tables. So there are 8 questions that come after. And you can answer those questions based off of this PowerPoint and the videos shown within. Let me know if you have any questions.